Imagine a cosmos defined by entropy, silent chemistry, and gravitational collapse. For billions of years, existence was blind, unfeeling, and purely mechanistic. Then, against astronomical odds, a sliver of matter started to look back. Not just to react, but to predict, to worry, to build entire worlds inside its own skull. This is the radical story of the evolution of intelligence. We often frame intelligence solely through the lens of human achievement, language, calculus, and space travel. But that perspective is misleading. Intelligence is fundamentally about information management, and its first appearance wasn't a spark of genius, but a gradual, relentless evolutionary arms race. What evolutionary pressure forced inert chemistry to develop complex strategies for survival? Today, we investigate the key tipping points, from the primordial sensor that distinguished light from shadow to the complex neocortex that allows us to contemplate our own origins. We seek to define not what intelligence is, but why it was necessary. The first phase of intelligence wasn't neural. It was chemical. Single-celled organisms, like bacteria, display remarkable intelligence. They navigate chemical gradients, form colonies, and delay growth in unfavorable conditions. This is computation without consciousness, the ability to process input and execute beneficial output. The defining innovation that paved the way for cognition was mobility. An organism that moves needs a brain to coordinate its actions and anticipate danger. The pressure to move fast, effectively, and safely required centralized information processing, the birth of the nervous system. Take the ancient cnidarians like jellyfish. Their intelligence is distributed in a nerve net, a decentralized system. While capable of sensing and reacting, they lack the ability to truly integrate complex sensory data. There is no self or command center, which limits learning capacity. The real analytical shift occurred during the Cambrian explosion, around 540 million years ago. This era saw the sudden appearance of complex body plans, driven primarily by the evolution of sight. Seeing required immediate, coordinated action, forcing the brain to become a predictive engine. The predator-prey arms race of the Cambrian era accelerated intelligence exponentially. If a predator can model the prey's next move, it survives. If the prey can model the predator's plan, it survives. Intelligence at this stage was a measure of predictive fidelity. This pressure led to two independent paths to high intelligence. The path of the vertebrates, protected by a skull and centralized nervous column, and the path of the cephalopods. Octopuses, lacking a spine and centralized protection, evolved unique cognitive mechanisms. Their nervous system is distributed, with 2/3 of their neurons located in their arms. They exhibit tool use, camouflage complexity, and puzzle solving, proving that complexity doesn't require a unified architecture. But the vertebrate brain, specifically the structure derived from fish and reptiles, offered the best architecture for scalability. The protected skull allowed for explosive growth, culminating in the three-part brain: the foundational arcomplex, the emotional limbic system, and the crowning achievement, the neocortex. The rise of mammals introduced the neocortex, a highly plastic, layered structure capable of mapping and remapping reality. Unlike prior structures, the neocortex is designed for abstraction, pattern recognition over time, and crucially, social modeling. It is the engine of adaptability. Social pressure became the new, intense evolutionary driver. Knowing where food is located is vital, but knowing who to trust, who to challenge, and who holds power requires significantly greater cognitive load. This is the Machiavellian intelligence hypothesis. The shift to bipedalism and the freeing of the hands created a profound feedback loop. Hands provided the ability to manipulate the environment with precision, feeding sensory data back into an increasingly sophisticated brain, accelerating tool use and innovation. The final, monumental tipping point that separated the Homo genus was the ability to handle abstraction. We didn't just understand the presence of a lion. We could conceptualize the spirit of the lion, the future hunt, or the tribe that existed long ago. This capacity was cemented by the development of sophisticated symbolic language. Language is not just communication. It is a compression algorithm for experience. It allows for the infinite combination of concepts, enabling us to share accumulated knowledge across generations with unprecedented fidelity. The cognitive revolution wasn't just about becoming smart. It was about externalizing our intelligence. Writing, mathematical notation, and digital systems are ways to offload cognitive burden, effectively turning our collective knowledge into a superorganism intelligence. This brings us to a crucial analytical question. Why did only one species, ours, achieve this level of generalized intelligence? The energy demands of the human brain are astronomical. It consumes 20% of our resting metabolic output. Evolution generally favors efficiency. The complexity was a high-risk gamble. The hypothesis suggests that our specific ecological niche, requiring simultaneous large-scale cooperation and intense environmental modeling during climate instability, made the high energy cost of abstract thought suddenly profitable. The ultimate lesson in the evolution of intelligence is that it is not a fixed hierarchy, but a landscape of solutions. The adaptability of the nervous system, its flexibility to pivot from instinct to abstract mapping, is its defining victory. As we stand on the cusp of creating truly autonomous artificial intelligence, we are forcing the next great leap in this evolutionary timeline. We are externalizing prediction and computation to non-biological systems. The definition of thought is expanding beyond the carbon-based brain. Understanding the trajectory of intelligence, from chemotaxis to supercomputers, is key to grasping our place in the cosmos. We are the improbable moment when matter achieved self-awareness. The great challenge now is ensuring that the intelligence we've developed, and the intelligence we are building, is directed towards sustained survival, rather than calculated self-destruction.